Thank you.
Thank you.
Yeah, so we're talking about chaos-driven development, or how you can apply test-driven development during the design and development of your distributed systems. My name's Tucker Vento. I lead the resilience engineering team and the reliability engineering guild at Bloomberg.
I'm Dhishan Amaranath. I'm part of public cloud engineering at Bloomberg, and I'm also part of the resilience guild promoting chaos engineering and resilience at Bloomberg.
As we both said, we work at Bloomberg, and at Bloomberg, we really care about reliability. We have over 7,000 software engineers. We maintain one of the largest private networks in the world, and as all these numbers indicate, we have a lot of data all the time. We're processing over 300 billion ticks, or real-time market data information per day, more than 15 million of those per second. If things go wrong, they go wrong in a big way. And our clients are doing what they consider to be very important things with this data. So it's important that we're giving them the right data at the right time. So reliability has always been important to Bloomberg, but over the past few years, we've been trying to formalize more of these things that we've taken for granted. And one of those things that we've tried to do more of is chaos engineering. And as we've gotten better at it, I think we've learned a lot of the same things that other firms have learned about chaos engineering. It's a great tool for shortening the time to having a resilient system. I'm not saying that you're not going to have a resilient system without it, but if you're waiting for things to happen in production and always responding to them, obviously that's going to take a lot of time. And we want to be proactive. We don't want to wait for the incidents to occur. We want to explore their effects on our own time. So chaos engineering allows us to shorten that feedback cycle and learn proactively from the same kind of scenarios that we would otherwise naturally encounter. But this second point is probably one of the most important for this talk. We've yet to run an experiment that doesn't teach us something, but oftentimes that something comes from just the planning of the experiment, not even running it. Obviously, this takes the time to be thoughtful about our experiments and carefully plan out what we expect to happen, but that's worth the effort. And chaos experiments run roughshod or more chaos than experiment, so it's worth the time. And finally, deliberately triggering these kinds of failures and measuring the response of the system allows us to codify our expectations for reliability and resilience as cleanly as, dare I say it, a unit test. And internally, our chaos engineering tools, they're tightly integrated with our monitoring, with our alerting, and triggering an expected alert is often the only way to get that green check mark at the end of your test. But why should we stop there? If we can treat our expectations for resilience as a unit that can be validated, can we do other unit test-like things with our chaos? And so enter everyone's least favorite development practice, test-driven development. It's been proven to be effective, but I use the word proven in quotes because it's also been proven not to be effective. I implore you to not waste your time reading these studies that I cite at the end of the presentation, because it's a great way to waste a day, but there's a lot of conflicting evidence out there. Many find that it leads to better code, many find that it leads to not better code, some find that it leads to worse code, but I don't really agree with that. But they agree on some things. All the scholars do tend to agree that test-first or test-driven development supports better program understanding. And this is very valuable for us because, as we've been learning all week, we can't maintain accurate mental models of the systems that we build. So any better understanding that we can gain is going to be very valuable. And the second point that they agree on is that the effectiveness of test-driven development relies on the accuracy and the usefulness of the tests that you're writing. And this is actually an exceptionally strong argument for chaos-driven development because we're not relying on tests that are synthetic. We're relying on accurate recreations of the real failure as they exist in the real world. I think we can all agree it's very easy to write a unit test that doesn't really test the thing that you think it does, but a chaos experiment tends to do what it says on the box. So what happens when we apply this to resilience? Here's the basic value proposition of TDD. We add a little bit more time to the development effort, but we save a lot of time in the QA stage. And for us, that's more like the productionization of the systems that we're building. And compared to traditional software development, the cost of QA really scales with the complexity that we're putting in our system. So any time we can be saving here is huge. So again, I ask, what happens when we apply this to resilience? And that's where we get resilience-first development. It may be chaos-driven, but it's resilience-first. And the real value we're going to get out of this, it looks very similar to all the lessons we've already been learning from chaos engineering, just a little more. We're going to have an even shorter time to having a resilient system. We're going to learn more about our system and learn sooner. And we're going to be able to apply that learning sooner in the development process. And finally, I cheated by calling them unit tests, but if we're shifting left our expectations for the resilience and the reliability of the system, we can treat resilience as a feature of the systems that we're building. And I don't think that's a really controversial idea to the people in this room, but imagine that it's not an afterthought. It's not just a last-minute summation of all of the failures that are present in your system. You're actually taking the time to lay this out proactively and try to codify what you expect to get.
All right. So far Tucker mentioned great ideas about why we need to do chaos experiment and what's the advantages of doing it early on in the life cycle, right? So I'm going to talk about our journey on how we used chaos experiments to build a highly resilient log aggregation architecture on public cloud. Right? Before I go into the advantages of doing this, I want to show you this architecture diagram on a dumbed down version of an architecture where how we do log aggregation, right? So we have the workloads on the left which are generating logs, and the logs are being processed by the log processor, which are pods in a Kubernetes cluster, and they're dumped into a centralized storage bucket. Right? So they're like primary and the secondary cluster. The health checks are being monitored, and alarm is configured to trigger a failover logic, which routes the traffic from the primary to the secondary cluster. Right? So nothing ingenious about this. It's a HA cluster for doing log aggregation. So now we wanted to actually test this, right? So this was in the early stages of development. We had a basic boilerplate here. So we actually wanted to test this. So to test this, we started thinking about chaos experiments. So the first step to actually write any chaos experiment or start triggering this experiment is actually asking the right questions. So they were immensely helpful for us. We started identifying missing pieces in our architecture. For example, the first question we asked was around how do we measure a steady state, right? So from the architecture, you see that like centralized storage bucket is one place for all the logs are being collected. So isn't this like a fantastic place to actually measure the overall health of your system? Why can't we have alerts here, right? We did not have metrics and alarms set up here. So we went back and configured our alarms. Similar to that, we started asking, okay, when we do these experiments, how can we actually monitor our system? Right, so do we have logging enabled in all the right places? So we went back and we saw that log processor actually emits a bunch of logs which are not being stored anywhere. Right? So what if the cluster goes down? Like, does somebody have visibility onto this? Right? And also it's also a catch-22 problem, right? It's a log processor. Where do we even process these logs, right? Where do we store them? And we started thinking in terms of like operationalizing for day 2. When this goes into production, right, the people who will be doing on-call, will they have the right access to see this? If the cluster goes down, where can they see the logs to, right? Similar to the failover logic. And since these are all in public cloud, we wanted to think through the solution, what we can use, so that for temporary troubleshooting and for long-term storage, where can we do all of this? It was not just about monitoring and logging part of things, right? So as we went through the checklist of experiments, we saw that there were some of these experiments like regional failures, right? What happens when the failover logic and the log processor, the primary cluster are in the same region? The whole architecture is void, right? We started thinking through this, and we re-architected some pieces of system here, and then we configured some of the system which does not have redundancies, for example, the centralized storage bucket here, right? So it's a central place. So it doesn't have any redundancies by default. So we went ahead and configured the HA configurations for the central bucket. So at the end, this was even before we started running any experiments, right? So we had an architecture which had all the bells and whistles, all the alarms in place, all the logging, monitoring setup, even before we actually started writing any experiments or started triggering any of these experiments. Before I explain further on what are the other advantages, I want to take a step back and explain how do we unit test a failover logic or unit test any of the architecture in a distributed system. So for example, I have taken one piece of the architecture here. This could be applied to anything. But the failover logic you see here is essentially being triggered by an alarm, which changes the load balancer backend pools to primary and the secondary cluster. So we introduced a mock event based on the documentation and tested the logic. We developed a logic. But to our surprise, when we actually tested this using the chaos experiment, we did actually node failure and a pod failure experiment, which dropped the health checks and the alarm was triggered. Right? The failover logic did not work as expected. So we realized the power of actually using the chaos experiments, injecting real failures to actually do a development instead of just mock events. Right? Mock events are still useful, but this is where the real power is. Right? So you're actually testing against the actual failure that might happen. So, and then I want to like further talk about like what are the other advantages we saw. So as we unit tested this architecture, we also tested the system as a whole. One of the major feedback we got during this process was actually confidence in our design choices. And in sometimes it's actually the lack of them, right? So finding faults in our design choices. Especially when you're doing this in public cloud, the sheer number of services and the configuration, it's very hard to get confidence from day one. right? So you don't want to wait for an outage to realize that what choice you made during your development is actually wrong, right? Let's see what we discovered, right? So the first one was actually where we too hasty to failover. So the experiment I showed earlier was around node failure and pod failure experiments, right? So when we did these experiments, we immediately did the failover, right? So it's a Kubernetes cluster. When a single node goes down, do we actually have to failover? No, it will manage it on the cloud, right? So it will spin up a new node or move the pods around, so your service is actually running. So we did not have to do that. So by doing this, we were able to establish the right set of thresholds to actually do a failover. The other example was actually using timestamps for file names. So when we process these logs, we use the timestamps of when it was processed, and we dump them into the storage bucket. So what happens when you introduced NTP faults into the system, right? There is a time offset, or for example, there are daylight saving time changes, right? So these things actually offsets the time, and then the files were overwritten, right, when we ran these experiments. So we went back and added some randomness into the name so that the files were never overwritten. This is something common we all face, right? As a developer, so I always go with, by default, go with defaults, right? So whatever's available in the public cloud, especially like when you have a lot of system, a lot of configurations, you go with the defaults. So, and it worked for us as when we did a functional testing. But the minute we introduced any application failures or API failures into the system, we realized that the defaults no longer satisfied our requirements, right? So they were no longer tolerant to our failures. So we went back, read the documentation, we tweaked our default settings, and we had a system that was better with the right set of defaults that works for us. We're not saying you won't discover this. We are not saying you won't discover this just through doing chaos experiment, right? But the thing is, at what point and what point in your life cycle you will discover this, right? So these problems may lay dormant on your system for many years to come, or probably like a daylight saving time, right? So you don't want to discover them at that point and go back to redesign your architecture. So it's about the point Agar mentioned, is like the development might take much longer when you do this test in early on, but the investment is great. Maybe it's a software or a platform. We always want to know the software limitations we have in the system. So this was one of the early advantages for us. The first one was actually with the application, right? So the log processor you saw in the architecture was an open source component. So it had some kind of retry logic and memory buffer against any of the downstream failures. So which impacted how long it took for us to realize there was a failure. So it was up to like 3 to 4 minutes, right? So we did not know this until we injected these failures. So we went back and tweaked some of the settings and realized that, okay, if this is something we can't deal with it, we at least have a better understanding of the SLOs we can offer to our own customers. Similar to that was the platform limitation. So since we are on public cloud, we were using multiple options that were already available, and we realized that there were like 3 to 4 minute delays before an alarm was triggered when the nodes went down, right? So we couldn't do anything about it, and we were okay with that as long as we had the necessary buffer settings or we had the necessary retry logics in place. So, but the revelation was that we could use this data, right? So we could use this understanding to design our workflows, to design our change management procedures such a way that we can circumvent all the limitations we have in the system from the day one. Right.
Thanks, Dhishan. So as reliability engineers, I think we understand that observability into our distributed systems is paramount to being able to make technical decisions about them, or at least informed decisions about them. But chaos engineering gives us a mechanism for validating that observability and strengthening our understanding. There's so many factors that contribute to the reliability of our systems, and not all of them are going to be in our control. But chaos engineering allows us to put those open source or third-party components to the test just the same as the ones we're building. And that allows us to make accommodating decisions and make sure that we can account for their failure modes. And as Dhishan was mentioning, the cost of delayed discovery about reliability defects can be monumental. It's the dark debt that Lauren mentioned yesterday, the insidious production issues that are lurking in the shadows. While this level of understanding is mandatory for mature system, the earlier we reach it in the development process, the more effective the rest of our development becomes. I'm not really a mathematician, and this may be an illegal use of the multiplication operator, but it makes sense to me. If we have better observability for more time, we're going to spend more time making better decisions. This is going to save us time in the long run and also just make us happy. So by shifting our chaos experimentation further to the left of the design and development process, I feel like we're setting ourselves up for continued success in the reliability and the resilience of our system. As we saw in our example, our SLOs are ultimately dependent on the availability of everything underneath us. And until we found the limits of those components, we may be operating under misinformed assumptions. The earlier we know about the limits of our availability, the earlier we can make, like I said, accommodating design decisions or make sure we're not giving unreasonable expectations to our clients that are following the development. And what I love about chaos engineering is the fullness of it. The premise focuses on validating the system as a whole, not any individual component. And so it can be applied to validate any change in that system. If we're forced to rethink one of our initial design decisions or otherwise come up with a new idea, we have an A/B test ready to go to gauge how effective that design will be. However, because those tests are so globally relevant, automation is going to be your friend, so you can continually assert your resilience as you're changing the system. And finally, the work we've done up front really serves as all the preparation we would typically be doing when it comes to production game days. So we treat chaos experiments the same as any other sort of software, and we want to roll them out in stages just the same. So by building this experimentation into our development process, by the time we're getting to production or any other later stage, we should be confident enough to start conducting experiments in that stage. So where do we go from here? I don't know who doesn't love a good checklist. We've come out of this process with what we think is a helpful checklist for new systems being designed and developed by our engineers. In a lot of cases, we were supposed to be asking these questions already. But it's easy to think you have an answer and then not think any more about it. So by backing these up with resilient stress tests or chaos experiments, we're really forcing ourselves to understand the answer. And not all these tests are going to be appropriate for every system, and some are going to be definitely harder to execute early in the development process than others, but we think it's critical for every scenario to be considered, and take the time to discuss them with your team and figure out what's relevant and what isn't. And we would err on the side of relevant if you're not sure. And if any of these scenarios don't make sense to you or you're terrified by this list, please come talk to us because we'd love to share more about how we harness failure to scare everyone else. And so where do you think you can go from here? Resilient stress tests should be part of certifying your designs. It may seem like a given, but our intent is tackling this earlier in the development process and setting us up for continued success. Day one, chaos accelerates all the identification of those things we pointed out earlier, just sooner, faster, better, all those words. And finally, we want you to break more things, learn more while doing it, and please have fun. Thank you.